Thanks for coming to the talk, and thanks for your interest in C++ testing techniques. My name is Zhang Yong. I'm a member of the testing technology team. My team is responsible for Google's testing infrastructures, like the automated testing daemon, the test coverage tools, and code dashboard. I'm based in Kirkland, so it's quite nice to be in the headquarters. My interest is mainly in developing tools for helping people to write better C++ tests. And today I'm going to talk about this in-house framework we made, which is called gMock. It's for writing C++ mock classes and using them in tests. Okay. First, let's take a look at what a typical C++ test is like. Usually, a test we'll try to first set up some stage by creating some objects and putting them into some proper states. And then the test will exercise the code you want to test. After that, you verify the result is expected, or you check the state of the system is in some acceptable state. And finally, you clean up after yourself. Okay. This is what we are all familiar with. And since this approach focuses on the state of the system and how a piece of code transforms that state, it's sometimes referred to as state-based testing. Okay. State-based testing is used every day at Google, and we know it works. And however, it has some limitations. Okay. So I think the biggest limitation of it is that it ignores the fact that C++ is an object-oriented language. We know that in an object-oriented program, we don't have just a single object. That's pretty rare. More likely, you are going to have many objects that talk to each other. Okay, so OOP is about collaboration between objects. Okay, those objects actually talk to each other by sending messages and responding to messages. So naturally, sometimes we want to be able to test how objects talk to each other. Okay. Oh, sorry, wrong button. We know that state-based testing is good for verifying how an object responds to a message. You just exercise that message and compare the result with what you expect. Okay, that part is simple. However, it's not a very good approach for testing how objects send out messages to others. One example is that we use a lot of logging in our system because proper logging is essential for debugging a server crash. So we want to make sure that the right information is logged at the right place, okay, and with the right proper information in there. And to test that, we basically want to verify that your production code sends the proper log message to the log system. Okay. State-based testing sometimes has some other problems. For example, if your code has some dependencies on some flaky components, then your test may end up being flaky. One example is that if you had to talk to the network, we know that a network is not always reliable. Also, your test can be very expensive if you rely on some expensive external resources like a database. Also, using state-based testing, it's hard to verify what the code does in case of a failure, because it may not be easy for you to simulate an error, like a file system error. You may have some code path in your program to handle a file read error, but how do you cause that part to be executed? It can be hard. Okay. To solve those problems, we need interaction-based testing. In interaction-based testing, the focus is no longer on the current state of the system. Instead, it tries to look at what messages are being sent in the system, and it also in order to do that, it needs to replace dependencies on real objects with dependency on test doubles. Test doubles are just objects that implement the same interface as a real object. However, it allows us to intercept the function calls, and we can do verification on the parameters and so on. once we have this test double injected in your code base, you can have your production code talk to the test double object, and that object can be taught to check the interaction between it and the object you are testing. And mock objects are a particularly effective technique in enabling interaction-based testing. So what is a mock? Obviously, a mock object has to implement the same interface as a real object. Okay, so you can use a mock object when a real object is expected. Also, you can control the behavior of a mock at runtime, such that you don't have to write a different mock class for each test, because you want to be able to configure the object to do different things based on the different requirements from different tests. Okay. And those objects know how to verify interactions on them. So if you tell a mock object that this method will be called with this parameter, then it knows to verify it when the function call actually occurs. How do you create a mock object? There are several different ways. You can certainly do it by hand, and it has been done in the past. However, it's not very pleasant, because it's usually a lot of work to come up with a mock object that is generic enough to be able to be reused in different tests. And that process is very tedious and error-prone. So as a result, many people just pretend there's no such problem, and they just avoid mocks. Okay. Clearly, computers are quite good at doing repetitious things. So why don't we ask the computer to create mocks for us? And this is perfectly reasonable. So we need some good tool to enable this practice. And for many languages like Java, we have some fine frameworks for creating mocks. Like there are two popular ones for Java, jMock and EasyMock. They use reflection of the language to dynamically create a mock object at runtime without any user intervention. Okay. So for C++, unfortunately, we didn't find any framework that's good enough. There was some effort, but the end result was not very usable. And we found that it has all sorts of ad hoc restrictions. So we decided to create our own, and the result is gMock. gMock was actually inspired a lot by jMock and EasyMock. Yet it's not a simple direct port from Java to C++. Some of the reason are because of the difference in the languages, like C++ doesn't have reflection. And at the same time, we also try to get the best parts from both frameworks and make them work in the context of C++. So we made many different design choices. Okay. So what does gMock give you? There are mainly two parts. The first is some macros for creating mock objects. Okay. After that, we provide a domain-specific language for you to configure the mock objects. By configure, I mean you want to be able to set expectations on the mock objects, meaning how it will be used, and what method will be called. And you also want to be able to set actions that should be taken once the method is invoked. Okay. Let's look at the macro for creating mocks. It's not just a single macro. It's actually a family of macros, but they are all similar. So the main macro is called mock method n, where n can be 0, 1, 2, and so on. And n is a number of arguments your function takes. Okay, so this macro actually creates a single mock implementation for a method in your interface. Okay, so it takes two arguments. The first one is the name. Here it's the name of the method. And the second argument is the type of the method. Okay. So you just declare your desire to create this mock, and gMock will expand this macro into its actual implementation. Here's a concrete example. Suppose you have this full interface. Here it has two virtual functions which are pure. The first one is do this. It takes no argument and returns void. The second do that takes an int n and a double x and returns a bool. So how do we create a mock class for this interface? Well, you just use a mock method for each method in the interface. So here it goes. So first, you define your mock full class as a subclass of this full interface. Okay? And then, for the first method, do this, you write a mock method 0. Remember that 0 here means this method takes 0 arguments. Okay. Now comes the interesting part. So for the type of the mock method, it's actually void parentheses. So what's this funny notation? Well, it turns out to be C++ way of saying that this is a function that takes no argument and returns void. Okay? And we do the same for do that. Okay? So it takes 2 arguments. So we write mock method 2 here. And for the type, we just write this returns bool and takes an int n and a double x. So as you may have figured out now, so the type of the method is actually obtained by dropping the method name from the signature. Okay? So in the complete signature of do that, you will have like bool do that int n double x. Here you just kill this do that name, and what's left is the type. Okay? So the process should be pretty straightforward, and I bet some Emacs hacker may be able to come up with an Emacs macro to do this automatically. Okay. So once you have this mock class, you can use it to create an instance of the mock object, just like you create other instances of other classes. Okay. Now that we have the mock class and we can create mock objects, how do we actually use them? Use a mock object. Well, before answering this question, I'd like to ask a different question. So instead of how we should be able to use it, how we should use it, I want to ask how we should be able to use it. So if you can design the perfect API, what would it look like? Okay. So I think a good API should address the user's concerns at the right level. It shouldn't be too detailed as to make the code look obscured. It shouldn't be too high level, such that you cannot express certain important things. In this API, we should be able to say which methods will be invoked, okay? And with what arguments. Also, how many times should a method be invoked? In which order? And what the method should do in response? Okay, those are the important things we want to be able to express. And we want to be able to express them concisely. Okay, let's look at a concrete example. So suppose this is something you want to test. You want to verify that this mock full objects do that method will be called where the parameter n should be positive, and it will be called twice. And then you want it to return true the first time and return false the second time. Okay, so here's the spec of the test. And here's how we translate it into the syntax of gMock. Okay, so the first part of the spec says this method will be called. Okay, that's fine. We write it in gMock. We say expect call this object and this method. Okay. Then we want to say that the first argument is positive, and we don't care about the second argument. In gMock, we just write do that with two things. The first thing is GT0 for greater than 0. And the second thing is just an underscore, which means we don't care what actual value it is. It can be anything. It's a wild card. Okay. And we want to say that the method will be called twice. OK. So in gMock, we see ×2. Okay. And then the actions. So it should return true the first time and false the second time. This is more verbose, but still pretty straightforward. So we say will once return true, followed by will once return false. Okay. Now let's put them together. Okay. So first, you create a mock object, and you specify the expectations. In this case, we have expect a call, mock foo. Do that with something greater than 0, and something whose value we don't care about. And it will be called 2 times, and will return true and false consecutively. Okay. After you set the expectations, you just exercise your code. In this case, you call the server object and ask it to do this XYZ operation. And you tell the object, tell the method to talk to this mock object instead of talking to its real dependency. Okay. That's all you have to do. You don't have to do the verification. gMock will do it for you. So the rest is completely automatic. By that, I mean if the method is called more times than expected, for example, if it's called for the third time, you will get an error report right away with the current stack trace. So you can debug. Also, if the method is called with some wrong arguments, you will also get error immediately. In the end, if all your code has finished and the destructor of the mock object is executed, if at that time some expectations haven't been satisfied yet, gMock will also find that and report it to you. So the syntax we have seen is pretty declarative. So instead of trying to express how you do the verification, it actually focuses on what should be verified. And it leaves the details to the implementation. Okay. Also, it has this benefit of it can report an error as soon as the error arises. So you can get access to the stack trace that contains the bug, which is very helpful. So let's sit back for a minute and think about how we would do this verification in the traditional state-based testing technique. If you use state-based testing, you will have to execute a piece of code and wait for it to finish, and then you compare the result. By that time, all those internal calls have returned, so you no longer have access to the call stack. That caused the violation. That leaves you in a very bad place to debug. That's why we want early report of errors. Now, let's take a closer look at the syntax of gMock. Here, inside the do that method, we have two things for specifying what arguments can be there. Okay, those are called matchers. We have seen 2 examples, and gMock has many more to offer. So what a matcher does is basically tells you whether a certain value is expected. So essentially, it's just a predicate. And indeed, you can use arbitrary predicate logic in a matcher. So the matching logic can be as complex as you want. As an extreme example, a matcher can also be a simple value. For example, 5 is a matcher which matches the value 5. Okay, so that's when you want to be exact. Okay, you can say that I just write the value directly. And like hello would be an example that matches the string hello. And that string only. Matchers are composable. That means You don't have to rely on those built-in methods. You can create new ones by combining all those building blocks. Here's one example. In this test, we use some code to drive a turtle on the screen. Suppose we are using a logo like graphics interface. Okay, so we want to tell the turtle to go to some place where the x coordinate is 0, but the y coordinate should be something that is both greater than 0 and less than 10. So you take two primitive methods, and then combine them using this all of combinator. Okay, that's how you create complex methods from simpler ones. Any questions at this point? Okay. Next, we want to specify how many times a method is called. For that, we need cardinalities. Okay. We have seen one example, which is times 2. And guess what? You don't have to be precise. Okay. You can say that I don't care about how many times it's actually called, as long as it's at least 3 times. Okay, you just write times at least 3. Okay, you can do that too. This is important in making sure that your test is not too tightly coupled with the current implementation. Suppose you have a test and some irrelevant change to the production code breaks it, you won't be very happy because you have to do work to fix that test. And that's what gives automated tests a bad name. Basically, people sometimes write tests that are too strict and they complain about automated testing doesn't work. Well, it's actually not that automated testing doesn't work. It's that you shouldn't be writing tests that are too tightly coupled with the implementation. And gMock offers some facilities for you to be right on spot. Okay. Also, we want to be able to specify what the mock method should do when it is invoked. That's called an action. Return true is an action we have seen. And in gMock, actions are optional, meaning that for brevity, sometimes you don't have to write the action explicitly in your expectation. If that's the case, gMock will try to find some default action when the method is invoked. And as a user, you have the option to define what that default behavior is. Okay. Here are some more examples of what you can do in a gMock action. So the first one works when the argument number n is a pointer. What it does is to assign this value to the object pointed to by this argument number n. Okay, so it only works in a function where the nth argument is a pointer and the type of the pointee matches the type of value. Okay. The second one is a composite action. So instead of just doing one single action, you do n actions in sequence. Okay, you do A1 followed by A2 and so on. And instead of doing each one of them for each invocation, you do all of them in a single invocation of the method. Okay. Also, you can return a reference to an object, or you can invoke any stub function. That means that the action can have very complex logic if you want. We talked about simulating failures earlier. Here's one example. Okay, suppose your code writes to the file system, okay, and you want to test how it handles a case where it cannot write to the file. And in order to do that, you set an expectation on this mock file object. Okay, you say, okay, write will be invoked at least 3 times. And suppose this write method returns the number of bytes it successfully writes to the disk. Okay? And then you want this method to return 256 the first time and the same the second time. However, from the third time on, you want it to return 0, meaning that it cannot write any byte to the disk. Okay, that's how you simulate an error. Then with this in place, and when you execute your production code, it will actually say a 0 returned from the file object, and the error handling pass will be executed, and you will be able to verify whether it does the right thing. Here's another real example taken from Google 3 code. Okay. We talked about testing logs. Here's how you do it. First, we create an instance of the scoped mock log class, which is provided by gMock. So what this class does is that in its constructor, it tells the log system, from this point on, whenever you see a message being logged, please send me a copy, because I want to intercept it and verify it. And in the destructor of this class, it tells the log system, OK, from this point on, don't bother sending me any of those messages, because I'm dying. OK, with that, then you can set expectations on this object. Here we have this log info, meaning that you will have an informational log generated by this source file. And the log message must contain this substring. Okay? And it has to be there at least once, but it can be more times. In that case, it will still pass the test. Okay. After you set the spec, you just execute the production code. And the verification is automatic. OK, questions so far? Yes?
How come you return a pointer to an object or a pointer to a mock object?
Sorry, could you repeat the question?
Is there a way to return a pointer to an object or a pointer to a mock object?
Where do you want to return that pointer?
Well, I have a rather complex set of classes I'm trying to test.
OK.
One of them returns a pointer to another one.
Can that be a mock object?
I can mock them all.
OK. So let me repeat the question. So the question was that if you have a complete or complex hierarchy of classes, and you want to test them, and one of the class wants to return something, and you want that thing to be a mock, is that possible? Right. That was the question. OK. Yeah. Yes, you can return anything from the production code. You can basically inject your mock objects into the production code using dependency injection or whatever technique you want to use. And you will be able to configure the production class to return either a real object pointer or a mock object pointer. And then you can, if you use a mock object, then you can set expectations on it and then have it verify the expectations. So did that answer your question?
Yeah, I'll probably email you later.
OK, that's fine. So we can talk more offline. OK, here's one more thing I want to tell you about gMock. Okay. What about order? Of course, right? So earlier we said that we want to be able to express in which order the function should be called. How do we do that? Here's one example. So suppose you have n expectations that need to be matched in the exact order they are defined. All you have to do is to put them inside a block, and you create an object of type in sequence in that block. Okay? So the actual name of that object is not significant because you don't actually use it. The real work is done in the constructor and destructor. So basically, this tells gMock everything in this block needs to occur in the strict order. Okay. What we have seen is an example of total order. And gMock allows you to define partial order as well. By that, I mean the order between some function calls may be relevant, while the order between some others may not be relevant. And you have the option to be as flexible as you want. I'm not going to show you how this works, what the actual syntax looks like. For that, I want you to just read the documentation, because I want you to have something to do after the talk. Okay? However, there's one thing I want to tell you now. So the syntax gMock uses, which is borrowed from jMock, actually guarantees that you cannot create a yield-formed ordering relationship, meaning that no matter what you do, it will always be acyclic. There cannot be circles created. So I think that's pretty nice. Also, you can express arbitrary directed acyclic graph. So as long as it's a graph and it's acyclic, it can be expressed using gMock. Okay, there's one last thing about gMock. So suppose you are not happy with what gMock has to offer today. Well, the good news is that it doesn't stand still. It can be extended by you, the users. Okay, so we provide an API for you to define your own matchers and your own cardinalities and your own actions. And once you define them, they can be used interchangeably with the built-in ones. So there's no difference in any way. So they work seamlessly with the framework, just as a built-in matchers and so on. So if you find there's a need that hasn't been filled, please write your own extension and share it with other gMock users in this company. We have seen how gMock works. Now I'd like to talk a little bit on how you can use it effectively. So if there's only one thing you remember from the talk, this is the one. Okay. This is the golden rule for using mocks. When you write your tests, you should always specify your intent precisely. No more, no less. By that, I mean sometimes we write tests that's too tightly coupled with implementation details. That gives us brittle tests. Okay. For example, if the actual value of a function parameter doesn't matter, you shouldn't specify it in the mock specification. Or if all it matters is that this value has a certain property, you shouldn't be specifying that this value has an exact value. You should be describing the property it has. And the same thing goes for cardinalities and order, of course. You should only be strict when it's important. That's one important way to avoid having brittle tests. On the other hand, your tests your specification should not be too loose either. Okay? If you are too lenient, you may end up having bugs creeping in without being caught by any tests. You don't want that to happen either. So you should always try to express precise intent in your test specification. I know it's not always easy to do so, but this is something at least you should be aiming at. That's a goal. And gMock provides some constructs that help you to achieve this goal. Next, I'm going to talk about some implementation techniques we used in gMock. We cannot possibly talk about everything, so I picked some things that I consider interesting. Okay. How do we implement this mock method macro? I mean, you just describe the interface, and the implementation is automatically generated. But there's a certain amount of thing going on under the hood. And what are they? Before answering this question, I'd like to ask a question first, which is, why do we use this syntax? Why not using a more obvious syntax like this? Okay. So instead of expressing the type of the method as a single argument, why don't we split it up? Like, okay, so we have separate arguments for the return type and for each argument type, like what we did for callbacks in Google 3. Okay. Well, the reasons turn out to be manifold, and I'm going to give you some main ones. The first is that not all types are created equal in C++. Like, for a simple type like int or char, you can declare a variable of that type by writing a name and to the right of the type, right? You cannot always do that. For example, here's a type, char, parenthesis, star, followed by parenthesis. So can someone tell me what this type is? Okay, so this is a function pointer, and it points to a function that takes no argument and returns a char. Okay. The problem is that if you want to declare a variable of this type, where should you write that variable's name? It's no longer after the type name, right? You have to do it right after the star here, in the middle of the type. So if you have this mock method macro take individual types as arguments, and you want to use this argument directly in building the implementation, you may be surprised when you declare a variable of that type. Okay, so that doesn't work. Another thing is that in a function declaration, a type may not be what it looks like. So we have a function f. It takes two parameters. The first is a const int. The second is char array of 5 elements. Okay. To the compiler, this signature actually means something not exactly like what we have seen. It actually means this. Okay. So for the compiler, the first parameter is actually just int. The const modifier is dropped silently. And the second argument is its type is actually taken as char star. It's no longer a char array. Okay, that's just how C and C++ work. So if you let the user specify the function parameter types and you use that type directly, you may be surprised that it doesn't match the real function parameter type. So we cannot do that. In this case, we don't want the original type in the parameter list. We want the decayed type, which the compiler wants. Okay. Another thing is that macros were introduced before we had templates in the language. That means that they don't play well together. For example, suppose you have a macro which takes a single argument, and you want to give it an argument which is a template type. It's a map from int to string. Okay. So can someone tell me what's wrong with this? Okay, so this won't actually parse. The reason is that the preprocessor and the compiler sees a comma here, and it thinks that, OK, here ends the first argument, and the rest is the second argument. So you end up with a macro that has 2 arguments. The first one is map less int. The second is string greater than, which doesn't make any sense. So the problem is that you cannot have unprotected commas in a macro argument. So if we do it naively, we will run into this problem. And the solution is to use the current syntax. Okay, here's how you do it. Note that we have this mock method has an argument which is a map. Okay, and there you have a comma here. However, this works because this comma is protected inside this pair of parentheses. Okay, so preprocessor is happy. Okay, And once this problem is solved, then we rely on template. OK, there's a question.
Return values that are template typed with commas?
That's a very good question. So in this case, we return a bool. That's fine. What if you return a map from int to string or something like that? Well, in that case, we have no way of preventing the compiler from complaining. So as a user, you have to do a type def on the return type, and then use that type def here. And basically, this is as good as we can get. Okay. But by putting all those parameters inside parentheses, we at least eliminate the majority of the case where you need these type defs. Yeah, that was a very good question. With this in place, we then use template metaprogramming to extract the types for those individual arguments. Okay. And the types we extracted will have no holes in it. So you can declare new variables using that types directly. And the types will be decayed by the compiler automatically. So that's what we want exactly. Another challenge is that we need to be able to mock methods that take different number of arguments. And their implementations are all different, although quite similar. So if you're not careful, you end up with a lot of duplicated code. And we have found that the TR1 tuple library is really handy in eliminate those duplicated code. So we were able to generalize the code such that it works with different tuple types. So you don't have to write different versions of the same code. And still, sometimes it's necessary to repeat code. And for that, we resort to a Python script, okay, which generates code at compile time. Actually, pre-compile time, we check in the generated code. Then comes the question, how do we implement the domain-specific language, or the DSL? Well, the DSL is nothing but some C++ expressions that has the look and feel of another language. But in the end, they are still C++. Okay? So the difference is that an ordinary C++ expression will do something when they are evaluated. For example, it may calculate some value, or it may cause some side effects. Instead, expression in the DSL, for example, an expect call expression in gMock, will just construct the abstract syntax tree from the expression without doing any actual work yet. Okay. With this AST, we can do some checking on it to ensure that it's valid. So we actually do both grammar checking and type checking on the AST. And some of the checking is done at compile time, while some is delayed to runtime. Here's an interesting thing. It turned out that we were able to actually do all the check-ins at compile time, all the important check-ins at compile time. Still, we decided to postpone some checking at runtime. And the main reason is that if you do it at compile time, then you leave the user to the mercy of the compiler's error messages. Okay? And in this case, it's tons of templates with no hope for any ordinary human being to understand. So we decided that at the cost of later error reporting, we want to put the error messages in our hands. So at runtime, we can generate whatever error message we want, and it can be very friendly and very informative. Once DSL expressions are checked, and when a mock method is invoked, the invocation will be intercepted and handed over to an interpreter. Okay. That interpreter will try to match the arguments and do the proper dispatching of the method calls. Next question is that just the same as DSL having a different syntax than ordinary C++ constructs, it also has somewhat different type system. Okay, so how do you actually encode that type system in C++ type system? Okay. And to see what I mean, here's an example. In gMock, the constructs are all statically typed, meaning that if you use an action in a run function, whose type is not compatible with the type of the action, you will get a compile error. Okay, that helps you to find the error early on. Okay. For example, the will once clause takes something of type action of f, where f is the type of the mock function. Okay. To complicate things, many of the actions are polymorphic, meaning that they can work in different types of functions. Take this most simple example, return 5. Okay, so what's the type of return 5? Apparently, it can be used in any function that returns a number, right? No matter it's an integer or a double. Okay, 5 can be interpreted as an integer or a double. Okay, however, it cannot be used in a function that returns, say, bool or a pointer. Okay, so we should be able to catch that at compile time. So the question is that how do you type this expression? What type should it have? It turned out that C++ type system doesn't allow you to express this polymorphism directly. However, there's a trick to simulate this effect. And here's how we do it. So at the bottom, this return x function generates a return action object. Okay, it's a template. So it's a return action of type t, where t is the type of x. Okay, so this return action class defined here is not actually an action. Note that it doesn't inherit from the action class. Okay, so itself is not an action. However, we define this type conversion operator, which allows us to convert this object to any action type that is valid for the context. Okay, so here, so this type conversion operator says that, okay, you can use this object as an action of f. Okay, so this is a template. And the body of the definition ensures that this class only compiles when the type of x here is compatible with the type of f here. Okay. So this worked out very nicely. Here's a more complex example. So we have a composite action which involves two actions. So the first action is to set the number one argument, the pointer of the number one argument to this number. And after that, we want to return true. Okay. So what can we tell about the function in which we can use this action? Okay. So from the first action, we can tell that this action must be in a function where the number one argument must point to something like a double, okay, or a float. And this function must return a bool. Okay, so gMock was actually able to combine those two pieces of information and make sure that this only compiles when you use this in a context where all the constraints are satisfied. Note that there's nowhere in the expression and you have to explicitly write the template type parameter, which is pretty nice, I think. Okay, here's the sales pitch part of the talk. Okay, we've seen how gMock works and how it's implemented. And here's the benefit of using it. It's not some kind of slick oil, but it helps you to do certain things really well. It allows you to test interactions between one object and its neighbors, which is not something that can be easily done using state-based testing. Also, by replacing dependencies on flaky objects with mocks, you can make your test robust. Okay. For example, instead of using a real network in your test, you can use some mock network that won't fail. Okay. And by replacing expensive external dependencies with mocks, you can make your test go fast. And also, it allows you to easily trigger failure conditions and test the failure cases. With gMock, there is one application outside of the area of testing, which is rapid prototyping. Okay. So before, suppose you are working on something that depends on a library another team is working on, you usually have to wait until that library takes shape before you can code your own thing. However, using a mock framework like gMock, you can start coding right away as long as you have the interface in the system agreed on. Okay. You don't have to wait for the other team to deliver their product. Okay. You can just start writing prototypes with the help of mocks. And people have observed that doing this actually helps you derive better design from your system because the process forces you to think in terms of interfaces, and that tends to lead to more modular code and more reusable code. Okay, so those are the benefits of the system. And when you go back to your desk today, don't just check your email. First, go to this website and check out the documents and try to use it in your tests and maybe prototypes. And keep your feedbacks sent to me. Okay, so I guess that's all I have to say. Any questions? No questions? Yes?
What are the plans to open source any of this?
So the question was, is there any plan to open source gMock? The answer is definitely yes. Currently, we are still running low on resources because I'm the only person working on this full-time. So I pull in help from other people, but they don't work on this as their full-time job. Also, gMock currently has some dependencies on other Google components, most noteworthy JUnit. So we need to make sure that works out first. And the good thing is that we also plan to open source JUnit. So the first step would be to actually open source JUnit, and then we can talk about open sourcing gMock. And if you are interested in help with the effort, please talk to me.
Is there any time frame for this? When JUnit may be open source?
So the question was, is there a time frame for open sourcing JUnit? So my OKR for this quarter includes making sure I understand what's involved in open sourcing JUnit because I've never done anything like that before. So it's a new process for me. So from that point on, I can be more certain about the actual amount of work it takes. So if you or some other members of the audience have more experience with open sourcing stuff at Google, please help me. Okay, any other questions? Maybe one question for you. So how many of you have already used the JUnit or gMock? Okay, there are 3 or 4 or 5 of them. Okay, for the rest of you, do you plan to use gMock? Okay, pretty good. Go back and talk to your teammates about this thing and have them try it and give me feedback. Thank you for coming.